interview, and they hit you with that question. A whole batch of chips is failing. What do? And your mind just goes blank? Well, if that's you, you are in exactly the right place. Think of this as your personal playbook for crushing those tough ATE debugging questions. We're going to give you a super clear, step-by-step framework that'll let you show off your problem-solving skills and, land that job.
So let's set the scene. You're on the production floor. A multi-million-dollar batch of chips is suddenly failing. The yield has just totally crashed. You can practically hear the alarms going off, the line has stopped, and yep, everyone is looking at you. So what do? The key here, and what interviewers are really looking for, isn't just one right answer. It's about showing you can handle that intense pressure with a calm, methodical approach. Let's break down exactly how you do that.
Okay, so here's our game plan. We're going to start with the absolute basics, connection and power. From there, we'll level up to the trickier stuff, functional and timing. Then zoom out to system-level issues. And finally, mechanical faults. And to wrap it all up, we'll talk about the most important piece of the puzzle, having the right debugger's mindset.
All right, let's dive right into our first section, connection and power. Look, before you even think about blaming the chip or the test program, you have to start here. You just have to. Is everything actually connected? Is it getting power? This is always step one, and it's the foundation for any solid debug process.
This is such a classic interview question. So, a device fails its continuity test. You might also hear this called an opens and shorts test. It's basically checking for any broken or short-circuited connections. A failure here is a massive red flag that something is physically broken somewhere in the path between the tester and the chip. The real question is, where do you even begin to look for that break?
So the problem can usually be narrowed down to one of four main areas. First, it could actually be the device itself. Maybe it got zapped by static or has an internal defect like a broken bond wire. Or it could be the socket that's holding the device. Those things get worn out, dirty, you name it. Then you've got the load board. That's the circuit board everything sits on. It could have a broken trace, or it could be something as simple as the handler or prober not lining things up correctly.
And this right here, this is the perfect, systematic way to answer. First, you figure out the scope of the problem. Is it failing on just one test site or all of them? If it's all of them, it's probably not a single bad chip, right? Next, you start isolating the variables. You grab a golden device, one you know for a fact is good, and you swap it in. If it still fails, boom, you've just proven the device isn't the problem. So now you move down the chain. You inspect the socket, maybe get out the microscope. Then you break out the multimeter and start checking the load board manually. It's all just a process of elimination. And see what we're doing here? We're already using that isolate principle from the debugger's mindset.
And that is the key takeaway you want to get across in an interview. It is not about making wild guesses. It's about having a repeatable, logical process to systematically hunt down the problem. You're showing your interviewer that you know how to tell the difference between a bad chip, a bad socket, a bad board, or a problem with the tester itself.
Okay, so we've covered the physical connections. Let's move up to the next level of complexity, the core logic and timing of the device itself. This is where we get into the real brains of the chip. And believe me, this is where debugging can get a lot trickier. Now this is a real head-scratcher of a scenario, isn't it? A device that was passing everything just fine suddenly starts failing a functional test. And the kicker, nobody touched the hardware, nobody changed the test program. This is a classic sign of what we call a marginal issue. Something is hovering right on that razor's edge between passing and failing. With these kinds of failures, we're not looking for a simple smoking gun like a broken wire. We're hunting for much more subtle culprits. We're talking about timing that might have drifted by just a few tiny picoseconds, or a little bit of electrical noise on the power supply. It could even be the device itself slowly degrading, or the tester hardware. So, to tackle these tricky issues, our debug approach has to level up too. First things first, can you make it fail again consistently? If it's an intermittent problem, you're almost certainly dealing with a margin issue. And that's when you bring out the big guns, characterization tools like timing and voltage sweeps. These tools generate these awesome visual maps called shmoo plots that show you the device's operating window. By looking at the shmoo, you can literally see if that window of good performance has shrunk. And that right there is the correlate principle in action. We're comparing what's happening now to a known good baseline. Okay, let's zoom out a bit. So far, we've been talking about debugging one device on one tester. But in the real world of high-volume manufacturing, you're managing a whole fleet of testers. And sometimes, you have to deal with failures that happen after the chip has already shipped to a customer. So here are two huge system-level problems you'll face.
A test escape is your worst nightmare. A bad part somehow passed all your tests and failed out in the field at the customer site. That's a major quality crisis. A correlation failure is more of an internal headache. That's when a perfectly good part passes on one tester but fails on another, which just tanks your yield and efficiency. As you can see, they have totally different impacts and require very different first steps.
When a customer calls and says a part failed, you can't just fix it and move on. No way. There's a formal, industry-standard process you have to follow. The whole goal is to understand exactly what went wrong, contain the problem so no more bad parts get out the door, and then put permanent fixes in place so it can never, ever happen again. This entire process gets documented in what's called an 8D report. It's a really structured, disciplined approach to problem solving.
And this right here, this is what separates a good engineer from a truly great one. It's not just about reacting to fires. It's about proactively preventing them in the first place. And that means doing rigorous reviews of your test coverage and using data to make sure your test limits are tight enough to catch these potential problems before they escape the factory.
We've covered the electrical side, the logical side, but let's not forget about the final physical link in the chain, the automation, the robotics that actually handled the devices.
A scenario like this is a giant clue. If the problem is happening on just one specific piece of equipment, but all the other identical setups are running fine, well, the problem is almost certainly with that one handler or how it's interfacing with the tester.
So the debug approach here, once again, is all about isolation. First, you use the data to prove that yes, the problem is really only on this one handler. Then you start physically inspecting things, the socket, the temperature controller, you name it. A really powerful trick is to manually load a device yourself, completely bypassing the robot arm. If that device suddenly passes the test, you have your smoking gun. The problem is definitely with the handler.
So we've walked through a bunch of different scenarios, right? But they all share a common thread. The real key here isn't just to memorize a checklist for every possible problem. It's about internalizing a universal problem-solving philosophy.
These core principles, this is the heart of the debugger's mindset. This is what should guide every single move you make. You isolate the variables to narrow down the problem. You validate your setup with a known good part to make sure you're not chasing ghosts. You correlate your results against the historical baseline to see what's actually changed. You always follow a systematic process, no random guessing. And finally, you know when to raise your hand and escalate, to bring in other experts when you need them.
So there you have it. That's your ATE debugging playbook.